Today is a little bit of a special event. We're quite pleased to be hosting tonight's workshop, which is one of a dozen that's being rolled out over the past 12 months through the National Energy Efficient Buildings Project, NEEB, which is managed by Sabina Douglas-Hill. Sabina, could you just acknowledgement to Sabina? Thank you very much for your work. Now this program has also been Sabina's also worked for the South Australian government to actually pull this program together. Now the NEEB started in 2012 and has been funded through the COAG National Energy Productivity Plan to deliver improved industry capacity to comply with energy efficiency requirements of the National Construction Code. During 2017 and also this year in 2018, this NEEB cross-industry skill training project has collaborated with over 25 industry groups to develop and deliver a dozen energy efficiency skills, courses, or videos for residential building designers, assessors, builders, and trades. All of them are available online, and today's course is being delivered by Sean and Thomas for about the 10th time, sort of nationally. And a lot of these resources, if you're interested, will be available on the ASBN website as well. Because we're doing two presentations back to back, I would like to introduce our speakers. For many years, Thomas has been a blower door instructor and has featured as a keynote speaker at numerous events for the wider building industry. Since 2006, he's been the general manager of Clima Australia and New Zealand. He is very determined and dedicated to turn things around in Australia and New Zealand and help provide the long-term solution that every family deserves, which is a warm, dry, healthy, and energy-efficient living. So welcome, Thomas. And then following out Thomas's act, we'll have Sean Maxwell, who is the technical manager of Clima Australia and the deputy chair of AERA's special technical group in building physics. His driving passion is the organization and elevation of Australia and New Zealand's community of building science professionals. And Sean is Australia and New Zealand partner of the International Airtightness Testing and Measurement Association. And he is also a national authority on the practice of building air tightness testing. Now, I would like to pass this mic over to Thomas, and I'll get your presentation up and going. Yay!
Thank you, Ken. Thank you for ASBN for organizing everything. So I also acknowledge everyone in the background that there's always lots of helping hands. Thanks to Brickworks. And thank you to you. Thank you for coming. Can we close the door so we're making sure nobody runs away? Before we kick off, quick question. Who is architect designer? Who's builder, building background? Engineers? And other trades? There would be? What do you do?
No. Hydraulic utensils.
Okay. And carpenter. Excellent. Okay, great. It's always good who we're talking with. And so, as Ken was saying, we're trying to do this interactive as possible. It's a real challenge, 20 minutes each. Normally we waffle on for hours on end. Sean already did 3.5 hours this afternoon, so that's why I'm kicking we got to kick off about some definitions. I'm an engineer, and I need to define things. So once I have actually defined things, then we can argue about things, and we can also agree to disagree in the end. So that's always good. How does water get into our external building fabric, into the walls and into the roof? Well, we have two different ways. We have what I call leaky building 1.0, which is the physical water just running straight in from the outside. Has anyone seen that? Oh. And then we have other things, which I call leaky building 2.0, which is actually also showing up as physical water in the wall, but it's the moisture from within condensing and then falling out. Who's seen that? Oh. Right. I think we have a very good audience, so you're aware of the situation and we can provide some solutions then going forward. Right, I will take you back in time now to the late 80s, and I'm originally from Germany, and we stuffed up colossal in the 80s. We stuffed in more insulation, and we literally stuffed up and created what's called sick building syndrome, maybe. And what happened was that in '89, Fraunhofer Institute of Building Physics wanted to find out what was actually going wrong in construction. And so normally what they do is then to go to sites, analyze, and try to find out what's going on. In this instance, they took 1 square meter out of an external wall, so a perfect 1 square meter, and they measured the R value of 1 square meter, and that was 89. The minimum requirement for insulation was then about 140 millimeter insulation in external walls in Germany. And they measured an R value of 3.3. Who thinks that makes sense? 140 millimeter insulation, R 3.3? Can you relate to that? Good. Okay. If I say something wrong, tell me. Okay. Then they said, well, we don't really have perfect walls because we always have imperfections. So we have like power plugs, lights, fittings, all sorts of things happening. So to simulate this, they just cut 1 millimeter through the internal lining for the length of that 1 meter. What do you think happened to the R value? Who thinks that increased it? Okay. Was there? Huh? There was someone drinking? Not. Who thought it's staying the same?
How many millimeters? 1.
There's just 1 millimeter cut through the internal lining. Who thinks it's the same? Still R 3.3? And who thinks it went down? What are the other people doing? Sleeping? So, by how much? What's your educated guess? You're a professional? You're going from 3.3, just a millimeter.
Yeah, I wouldn't have a clue, to be quite honest. A millimeter, cut through, yeah.
Just anyone?
3.
Down to $50? So we got 3 for the first one. Anyone else offering something?
1.
$2,000. Oh, somehow we need to pay for our flights, huh? 0.7. And we know this. If you wear a nice woolen top, jersey, and it's really windy, do you feel warm or cold?
Cold.
Cold. What's the insulating part of insulation?
Trapped air.
Correct. And if you have airflow through, you have no R value. Right. That was easy. Everyone knows that. We can experience this. Then they said, well, we have a problem with moisture. So again, 1 perfect square meter. And they measured the moisture going from the inside out under these European climate conditions with a bit of pressure on it. But they measured 0.5 grams per square meter a day going out in terms of water vapor. Yeah? And that's what we call diffusion. So that's moisture migration through materials from a higher level to a lower level. Does it still make sense? Good. And then we repeated the experiment by cutting a millimeter through that plasterboard again for the length of that meter. What do you think happened? What did they measure? Who thinks it went down? Who thinks it stays the same? Who thinks it got worse? Any takers? So we're at 0.5 grams per square. 350. $10,000. Are you sure? Any other takers? 800. It's about a liter. And this is what we call convection. So we can move moisture in different ways. We can have it through diffusion, so through the actual building material, or we can have airflow. And I experienced that yesterday afternoon when I flew into Adelaide. So I went to the gents at the airport, and then was this sort of Dyson super blade, dry. So we know with warm air we can move massive amount of moisture very quickly. Still make sense? Good. If anyone wants to disagree with me, happy to do that. Well, what we need to do in terms of moisture control, we need to start off with really stopping that warm airflow through our building envelope, and that's where we normally relate to airtightness, so draft stopping, and I will leave it up to Sean to go in more detail around airtightness. And the other thing we need to look into is what are we doing about this diffusion, the moisture migration through the building material. Who has heard about diffusion before? At uni at some point? Yeah, and then long forgotten about it. But this is hitting you every day in the building industry, and you need to be aware of that. So what we need to look into is what can we do to prevent extra moisture going into our construction, and how much drying capacity we have back out. What's the easiest way of rotting timber? To put it between two plastic sheets, because you make the assumption that it stays nice and dry because it prevents the moisture from both sides. The reality is moisture finds its way in, and then it's trapped and it rots away. If you don't believe me, try it out yourself. Trust me. And how does it actually all work, and how do I know it works? Well, the way that we normally do things in regards to moisture is we use sophisticated software simulation tool. And in this instance, we use WFI. And WFI stands, does anyone know what WFI stands for? Anyone? Wärme und Feuchte instationär. So, 1, 2, 3. Wärme und Feuchte instationär. Excellent. You already won a prize there. Thank you. Wärme und Feuchte instationär basically means that what it does, it simulates the heat flow and moisture flow through the building assembly based on real climate data and real material data. Yeah, so unfortunately, this will come your way big time. I'm not saying that you will be doing those simulations. It will be a separate profession, will be engineers who will be doing that and delivering, but you need to know the background. And the other thing, airtightness is very simple. Well, we just basically do our blower door test. We can organize another blower door demonstration then? Oh, we've got Jessica. Where are you? There. We'll see you later on stage. Good. Talking about. Right, WFI stands for? You're not going to get a prize, Sean. And this is really what it then looks like. So the interesting thing with any kind of software simulation tools is that you need to understand what it does. Yeah, with any IT software. So garbage in, garbage out. I can prove that Adelaide is on the moon and all sorts of things, and the Earth is flat. Well, we should talk about it. And this happened again in the 80s and 90s. This is actually a title of, coincidentally, of a bricklaying magazine in the US. And they were afraid of what's coming their way because they thought it's have a negative impact on things. And so this is what WFI does. Looks complicated? Not really. What we have here is basically we're loading up the construction with moistures in different forms. So we have physical water, rain coming in. We have condensation forming from outside, inside. And one thing that I've seen in Australia a lot is built-in moisture. I've seen houses framing on building sites that were soaking wet before they even lined it. So I haven't told you about it, but I have this idea of getting little stickers made, like sort of like guerrilla marketing type thing, where we write down the date when we were on site and our free 1-800 number and say, call us in 5 years when you find this sticker, when you open the walls, because it's riddled with mold. This is unbelievable. We're creating a disaster. Who has heard about the leaky building crisis in New Zealand? Yeah. And everyone talks about, oh, it's physical water running in. Well, yes, that's part of it, but it's also this stuff here, condensation, all three of them. And then, of course, we hopefully have drying capacity. So we can shed water away. That's our first layer of defense. Then we have evaporation and airflow. I talked about convection, a way of moisture to be transported. It can be negative, but can also be positive. So when you actually have a capacity there for air to be transported away, then it's positive. Has anyone seen proper ventilated cavities in Adelaide? Or just drainage cavities? Or no cavities? No cavities? Okay. Direct fixed EPS? How's that going? Yeah. But, and then basically what we also want is a safety margin built into the whole thing. So that when our drying capacity suddenly sort of doesn't work anymore, that we at least have a bit of built-in. As engineers, sorry, I was you said, my background is structural engineering and building physics, so heat flow, moisture flow, acoustics, and fire. And if someone asked my opinion about what the level of what my comfortable level is, I would say, well, this is your minimum requirement of the code. Then sort of the firm's liability level, and my level is here. Under no circumstances, I want to be responsible for mold and condensation, and in the end, structural deterioration, because I didn't do my job properly. Yeah? And that's why you pay engineers a lot of money. And this is often what we find in reality. We have a lot of wetting through convection, through physical water running in. We just saw some beautiful photos of a flood, of a house that was flooded, and then it was really hot as well, and it's just perfect breeding ground for mold. Yeah? And, and we don't have here any drying capacity, so it means that our safety margin we build in is not high enough, and the whole thing tips over. Yeah? Does that make sense? So WUFI stands for? I can't give you half a prize. Everyone keeps practicing, and hopefully by the Q&A session we have another prize to give away. Sorry?
What's the translation?
WUFI, so the question is about what's the translation of WUFI, and WUFI, Erwärmung, Feuchte, Instationär, stands for intrinsic moisture and heat flow. So who has heard about glazer or glazer? Are you in the building industry? Sorry. So this will come your way. So what we're talking about tonight, and Sean will be taking over with the blower door soon, is really about talking about these two fundamentals that we need to look into before we build. So WUFI is a tool that's normally used during the design phase. And the good thing is you can substitute individual layers and rerun the simulation very quickly. It takes you a minute to do that, to identify what your safety margin is. I'm not saying please use this tool to find out what you get away with, yeah? Because we have the complexity of the different materials interacting with each other, we have the local climate conditions, and then we have the skill set of the applicators as well. So you want to make sure that you have a bit of, and design issues. So you want to make sure you have sort of a safety margin built into. And that's done before we build. Normally what we find in Australia at the moment, we still do what we call field test. So you build a house, design, build a house, and after 5 years or 10 years you figure out it didn't work. It's very costly. Yeah? We've done the same thing in all sorts of countries around the world. So what we do now, we simulate before we build. Yeah? And then while we're building, we do the quality control while we're going through that process with the blower door, and that's what Sean is going to talk about. Okay? So far so good? Still interested? Okay. Right, I'll come to the end. So from our end, the key thing that I really want to get across is that please design from the beginning so that we don't look into the issues of leaky building 1.0 and 2.0. So that means to have proper weatherproofing on the exterior. And if you want to know more about detailing, happy to discuss that as well. And also sorting out the moisture from the inside with airtightness, which Sean is going to talk about, and the diffusion where you can simulate with WUFI. And there's different options of how you get to it. Then the next thing you really want to do is specify a correct internal layer, and if you want to talk about it more, I can tell you there's like a special layer that we currently do not do in New Zealand, in Australia here, which is a layer that's installed between the internal lining, which is normally plasterboard, and your insulation layer. again, we can talk about more in detail in the Q&A session. And that sort of creates your air tightness layer and also the moisture control layer. Then, of course, we want to do the woofie simulation, which stands for? Oh, not bad. Can you pass it on, please? Wärme und Feuchte instationär. Very good. And then blower door. Oh. There's actually no German translation for blower door. So I'm trying to retranslate it. I can't think of a word. And so all these together then actually enable you to design and build a proper building envelope. If you want to know more about what help we can offer, so we offer a free service. So if you have some plans, you can send them through, and Sean will come back with red marking everywhere. Not everywhere, but our job is really to provide as much knowledge transfer as we can do. So thank you very much for coming to the session tonight, and I hope that Sean will continue to inspire you and not just irritate you like I did, hopefully, not just. And I'll just hand over to Mr. Blower Door. Thank you.
I'm Sean Maxwell. I am president of the Air Infiltration and Ventilation Association of Australia. It's the most important organization in Australia. Just kidding. So, my passion, my history is from the US. My first job was doing blower door testing. So, this is what a blower door test looks like. I'm going to talk to you about blower door testing in general, and then about some air tightness things that you can do with your next project, and talk just in general terms about air tightness. So I'm not going to get too scientific about any of it. That's what I actually like about a blower door test. It's not that complicated, really. So has anybody, you raised your hands before to say who has seen a blower door test, who hasn't seen a blower door test before? Can you guess what a blower door, why it's called a blower door test?
You blow some air.
You blow some air. It's a blower in a door. It's really complicated. So see that fabric frame there? You erect this temporary frame, and you put this big fan in it, that's the blower, and use that fan to produce airflow, and that makes pressure on the building envelope. Well, airflow in equals airflow out, or rather airflow out equals airflow in, and you can measure that and do this repeatedly on this house and then the next house and then the next house. It's so simple that this is building code in much of the developed world. So probably half the population of the US lives in a state where it's required by code to get your certificate of occupancy. Now today I learned that certificate of occupancy actually isn't a thing in some parts of Australia. Well, it's a thing in America where you have to get signed off that yes, you met all the requirements, and the building inspector, who is employed by the state, not privately employed, has to sign off on it and say, yes, you met those standards. So I'm not going to brag too much about the US right now, but I will say that blower door testing is accepted in some states. So simply put, it's a very coarse assessment of building envelope integrity. So you hook a fan up to this digital manometer, which is a pressure gauge, and it measures the pressure between inside and outside. It measures the flow, and it uses a computer program to do a pretty simple logarithmic exponential calculation to find what the airflow would be at any given pressure. And the pressure that everyone talks about is 50 pascals. 50 pascals is like the pressure exerted by, say, a 33 kilometer per hour wind on the side of your house. That's 50 pascals, so it's not crazy. But it's more than ambient pressure, so it's high enough that it overrides a lot of the interfering factors. So this is so well sorted out that in the UK, they have a thing called the Air Tightness Testing and Measurement Association, which we in Australia are joining. Atma, they've sorted out a lot of the details about this and made themselves very amenable to regulation because they have an online database that you can submit your results to. It checks for data quality and then spits out a standard certificate that can be checked by your building inspector, and it just spits out a number. That's the beauty of a blower door. Okay, so a blower door induces a pressure on the building envelope, and that makes airflow in or out. Under suction, when you blow air out of the building with a blower door, it makes air come in through all the gaps and cracks. So with an infrared camera, I've got an infrared attachment on my phone, which you can take your infrared selfie with later. It shows you heat flow. And when you have air leakage flowing in and out of leaks, that leaves a trace where the air leaking in steals heat from the things that it touches, and you can see those fingers of air leakage on the walls. So that's what these dark streaks are. They're air leaks stealing heat as they come in. It's powerful because it allows you to, the combination of blower door and infrared allows you to see things that you couldn't see before, and it allows you to go places that you couldn't go before. So this is, I did a blower door test of a large refrigerated warehouse. Up in this corner up there, I wanted to know, is that leaking or not? Because I want to know, everything else in here is pretty airtight, but is that going to leak? Well, under positive pressure, I'm pushing air from this cool warehouse in through that leak there. So it doesn't show up because everything's the same temperature. But when I turn it to negative pressure, I suck air in, warm air from outside is coming in that crack, and as it comes in, it warms the crack, and you can see that warmth, okay? You can see the warmth there coming in through the crack. We'll go to the next slide now. So, air pressures on buildings include lots of different factors acting on the same building envelope. So, wind is one, an obvious one that everyone can understand. Stack effect is the tendency of warm air to rise and pull with it cool air in from underneath to replace it. Mechanical systems exert pressures on the building envelope. It could be positive, it could be negative pressure. Sometimes that's by design, sometimes that's by accident. And they all combine to make air transfer through the building, through the envelope, and then through spaces in between. So here is one of them in more detail that everyone can experiment with themselves. This is called stack effect. It's very important to a building scientist. Stack effect is basically, it's like the tendency of a hot air balloon to want to rise. And the reason it wants to rise is because the air in the balloon is less dense than all the colder air around it. And so as a result, that colder air is going to want to suck in below, and the warm air from the hot air balloon is wanting to rise above. So that's what happens when you have warmth in your house on a cold winter day. That is trying to pull up, and that's putting positive pressure at the top of the building. And then the cold air that wants to leak in to the bottom of the house, the suction on the bottom of the house is negative pressure. So positive at the top, negative at the bottom. That's stack effect in the winter. These dynamics are the reverse in the summertime. So negative at the top and positive at the bottom. It's like a pot of water that has a leak in the bottom. That more dense water is wanting to leak out the bottom, and it's replaced by less dense air at the top. All right. So let's talk about regulation of these very important things. So here's what the National Construction Code of Australia has. Really, really rock solid language, like a roof light must be sealed or capable of being sealed. Like, you could look at the roof light and say, that's definitely capable of being sealed. I'm not sure how if you're a building inspector or government or regulation, how you're actually going to enforce that. And there's also lots of other ridiculous language, like this must be constructed to minimize air leakage and restrict air infiltration. It's just silly, just totally useless. Sorry, I didn't mean to mess up your picture there, but that presumes that air is leaking through discrete leakage paths, like fans, like light switches, like this leak around this bathroom fan. You see this brown here? That's from dust leaking up through this, humidity as well, causing mold to grow on the insulation around this bathroom fan here. All this black here is dust leaking up through that crack around the light switch. But that presumes that everything can sort of fit into this checklist of stuff that you have to be sealed. Well, real buildings are more complicated than that. So other leakage paths like this leak around this sliding door here, or this leak around this skirting here at the bottom of this board in the closet, it's difficult to make a list for every single leakage path that there is. So the blower door basically gets rid of this qualitative opinion about whether something is sealed or is not sealed or capable of being sealed, and it just gives you a number. And for a builder, that's kind of liberating, actually, because you say, all right, I don't care about all this stuff that you're telling me I have to do. Just tell me what number I need to meet. 10 is what's being proposed for the National Construction Code 2019 as an option, not mandatory, it's an option. They say, all right, 10, all right, let me see what I can do to get to 10. And if I get to 11 and I need to get down, maybe I can do a couple things to fix that. But the beauty of the blower door number is that it's a yes or a no, whether it's passing or not passing. It's not an opinion about some guy or girl who is evaluating whether you've made something capable of being sealed. The other cool thing is that it's pretty well established and regulated. So this is a ATMA standard certificate from ATMA Lodgement. That's their online database. You submit the results right then and there, and it automatically does data checks on it to say, does this make sense? Some pretty simple things that can tell you whether a test is real or not, and whether the test results are the same as one that you've already submitted. It's pretty simple quality check that you can do. So some specific leaks that you can look for. I won't spend too much time on this because you all are involved in super advanced buildings. But these are some common ones that I see in less advanced buildings, like this leak above this in this kitchen here. The builder said, I said, what is that vent there for? And he said, oh, that's in case the bath upstairs gets a leak. I want to be able to fix it. And I said, don't they make opaque panels that you can to do that? And he goes, no, they don't make those. Yes, they do make those, guy. So there I am measuring the leakage of that dumb leak. Here's another one. This door to missing door weather seal there. Little bugs can crawl in there. Airtightness is not just about energy. It's also about comfort and pest control and acoustics. So some things, just because you can't see it, doesn't mean it doesn't exist. So this crack here in this corner, just because you can't see it doesn't mean when I run my hand along there during the blower door test, it's leaking really badly. And so fixing that is just a matter of using some caulk. It's not very complicated. Some things, the building code requires this stuff, like it says that an exhaust fan must be fitted with a self-closing damper. This one is an energy-saving exhaust fan, apparently. Well, 95% of the fans that are available in Bunnings don't have the code-required damper. You can buy them, but almost nothing is, most of those fans aren't even compatible with ductwork, which you could use to hook up to this damper on the outside of your building. When the fan is off, you don't want it to be leaking your building air, right? Because otherwise, it's just wasting energy for 99% of its life. Some of these things, like cavity slider doors, aren't actually that difficult to conquer. So the door assembly itself is it's filled with, it's very hollow structure and full of holes. But if you just use caulk or a gasket here or some foam around the assembly, you can make a pretty airtight structure to enclose that leak pretty easily and very cheaply. So not all this stuff is difficult. Some things like this leak here, this porch attached to this 2-story house, I look at this and I think, that's going to be bad. And sure enough, I walk up to it, and these joists, just because of the way the framing goes, are penetrating the air barrier or the thermal envelope of this building. And for the entire life of this building, they're going to be leaking massive amounts of air. So it's easy stuff to fix. Just with some foam boards and some foam around there, this is not expensive. I'm a fan of trying to find for the regular code home builder to find the cheapest way to accomplish what you need to accomplish. So doing a big building is nothing more complicated than more fans. And now we've got very cool, oh, darn it. I meant to replace my picture with Jess. I have a picture of Jess using this. Where is that picture? I don't have it. Jess doing the blower door test on this, doing this blower door test on this building the other day. Jess, well, she's actually wearing it right now. Jess, you'll be up here later, but please flutter your air leakage detection scarf. So it's got lots of filaments on it. It's very fashionable. So she can go right up next to an air leak, and the scarf goes and just flows with the negative pressure there. It's really, really poetic. So using tools like a manometer and a manometer hose there, you can look this leak here. We're standing right now on a balcony outside the building. So this pole here, we're outside the building. We're doing a blower door test. This pole should not be leaking. Why is the pole leaking? I don't know. Well, we have to find out. But Mark put this hose in the hole. Mark put his hose in the hole, and then when he did that, he noticed a lot of negative pressure. That negative pressure means, sorry, the blower door innuendos just don't stop. There's suction on that hole. And as a result, that tells you that there's air flowing in through the hole. It's a big hole and a lot of suction in that big hole. So that means that there's a large volume of air moving through there. So this is a significant leakage pathway. So where this is meant for, on the other side, there's electrical switches here. So that's what this is for. It's meant for service, electrical service on this balcony. But wherever that terminates, wherever it ends and goes into the thermal envelope, it's probably completely unsealed, and that's why it's leaking that much. So fixing this is probably not that difficult. It just means lifting up a drop ceiling somewhere and looking for where that thing comes in, a bunch of spray foam there, and the problem is fixed. But big buildings, little buildings, it's actually pretty simple, the fixes and diagnostics of this stuff. So we are going to do, during the break, a red pen test. So a red pen test is something you all should do on every single project you're involved in. The red pen is this red pencil that some of you have. I'm going to give someone else a red pencil right now. Someone? Do you want a red pencil, sir? Catch it. All right, so the red pencil, this is the exercise that you have. Take that plan that you have, draw a red mark around where you think the air barrier in this building enclosure is. And we're going to talk about what that means. It's the cheapest air barrier you can make is made out of building paper, building plans. It's so much easier to catch problems at this stage than it is to catch them once the building is under construction. So do this during the break, and we'll get a chance to talk about this afterwards. Thanks.
Now, We're going to be going into some of our favorite part of our events, which is a Q&A. We really don't know which way this goes, and that's why you guys are a part of this ride. You guys are going to be in the driver's seat. Who has the burning question that they want to get off their chest? Oh, we got one all the way on the right side of the room. If we could please over there. And now, sir, what's the first question you'd like to kick us off for? And please project your voice.
Given that Australia still builds home that leak a hell of a lot, so even with blower door tests, 30 air exchanges per hour is not unusual in new builds. 16 is the average. What level of air exchanges for ventilation do you see as being optimal for Australia? I don't buy that the 0.6 of the European countries is what Australia needs, but I'm hoping that we're going to achieve something less than 16.
Everyone heard the question, right? It's about sort of what levels of ventilation do we need to in terms of, or in comparison to air tightness. First thing is that we need to clearly, sorry, being the engineer again, we need to define what we're actually talking about. The first thing is we talk about infiltration. Infiltration is the uncontrolled airflow through our building fabric. Yeah? So we're looking at building, and it's the airflow through there. And what drives this airflow?
Stack effect.
Stack effect, excellent. So we have stack. And what else? Wind. Excellent. Wind. So that's a random act that happens depending on what Mother Nature throws at the building. Do we agree with that? Yeah, good. So, and then we have ventilation. Ventilation. Sorry, you can't see it at the back. Huh? Ventilation is basically there to replace your stale air on the inside with fresh air from the outside. Do we agree on that as well? Okay. So these two things are totally separate from each other. We do not want infiltration. We do not want to have uncontrolled airflow through our building fabric because of moisture, condensation, da-da-da-da-da. Also, I don't think anyone in their right mind wants to inhale air that passed through the building fabric plus whatever was there. That's not considered as fresh air. Fresh air is from the outside. So coming back to your question, ideally, for our ACH 50, we want to have zero, no airflow through the building fabric. For ventilation, the World Health Organization recommends about sort of 0.3 ACH, but not ACH 50. What it means is that every 3 hours, we want to replace our stale air on the inside with fresh outside air. And how do we do that? Opening windows and doors. That's the traditional way. Nobody does that anymore. So now we're looking into some form of forced ventilation. Because with infiltration, if you have 20 degrees on the inside, 20 degrees on the outside, how much infiltration is happening with no wind? Nothing. But we still need to provide fresh air on the inside. So we need to go down the path of some form of forced air movement. And we just had this discussion with a gentleman before that a mechanical ventilation system doesn't mean you have to spend $10,000s of dollars. The cheapest mechanical ventilation system is you have a louver system on one side and an extraction fan on the other side. Costs you, I don't know, $30. And then it's a DC motor that maybe draws 30 watts. That's what, $60 a year. That's it. And then you can have the Rolls Royce, like the balanced heat recovery ventilation system with 95% energy efficiency core. Yeah? But it's important to understand infiltration and ventilation are something completely different. Did I answer your question? So your question was rate. 0 ACH 50. We never get to that. But 0.3 air changes per hour. Hope that makes. Is that okay? Understood? Good. Thank you.
And I'd just like to throw in here, I was rude and didn't actually introduce our guest panel member, Jessica Allen. I apologize about that, Jess. I'm just trying to blow in through to the Q&A. But Jessica Allen is a sustainability consultant at Sustainability House, well, SUHO, and she specializes in building envelope audits using blower door testings and thermography. So she's bringing a lot of local expertise to the table in our Q&A session as well. Was there anything that you, Jess or Sean, you wanted to add to, if there is a target that we're trying to meet, like, where do we need to go?
Sure. Jess and I were talking about this earlier. So some standards for ventilation, so ASHRAE 62, for example, says below a certain level of air tightness, you need ventilation. Above that level of air tightness, it's not even worth it because you're getting enough air leakage from just normal processes. So like above 7 air changes per hour, or a permeability of 7 cubic meters per hour per square meter, it's not even worth it because there's so much air leaking out of your building anyway, who cares? So below that, there's recommendations for what you should do, say a simple ventilation system down to a level of 3. And below that, you should then invest in heat recovery ventilation. What I think is necessary for Australia, what would be beneficial in terms of cost effectiveness for air tightness, I think the passive house level of 0.6 is probably for the general population of Australia. To get to net zero, that's my goal. To get to net zero, I think that for many climates in Australia, that's probably overkill. For some climates in Australia, that's not overkill at all. Like, some climates you should get even tighter than that. But we do need to find some balance point for this, but the balance point always is probably below 2, 1 air change per hour, something like that. And that's where the energy balance evens out.
Anything to add to that, Jess?
I did have something.
Yep.
Perhaps to answer your question in a different way, to put a more realistic spin on it, in terms of air changes, you want to aim for between about 7 and 10. Like if you've got an existing house that's blowing 30 air changes, if you want to go around and try to do the best you can to seal it up, you want to aim for about 7 to 10. That's sort of a level where you're not leaking tons and tons of air out of your building fabric, but you also aren't required to add mechanical ventilation. Does that answer your question?
So I think we also need to be mindful that we are not misunderstanding the drive for higher and energy efficient buildings. So when you're talking about very low levels of infiltration, so the uncontrolled airflow through the building envelope, it doesn't mean you're not allowed to open up windows and doors. That's sort of a misconception. We have a very sort of outdoor lifestyle where we want to go in and out all the time. But to be honest, like if the sun goes down and the bugs come out, I better make sure I close the door because I don't want to have that stuff. And then that's where the mechanical ventilation system can kick in. Or when it's really hot outside, the last thing I want to do is leave my windows and doors open. I had the joy of seeing a family that just recently built a certified passive house in Canberra, in ACT. And so I went in there and the kids were running around and I was talking to the lady of the house and said, how's it going? Oh, it's beautiful. We can run around in shorts and t-shirts in the middle of winter and we have no heating going. It's all good. And I said, oh, great. And what's your biggest problem? She said, we can't hear the birds anymore. So I opened the window.
And we'll just get to you, Tim, but we also, there's been a little bit of discussion on, okay, you create quite airtight buildings, but they still aren't properly designed for climate. So maybe they don't take in consideration orientation, properly shading, or even things around maybe even like thermal mass or even insulation levels and things like that. If we create a lot of airtight buildings that aren't well designed, will that also be a problem? Maybe because of like overheating or different things like that.
Yes, we can create more problems, but it's less related to airtime, it's more about insulation. So if you not everyone has the luxury to design the building to the orientation we'd like to because it's of constraints of building sites. But what is definitely necessary is external shading. I mean, if you just create a hot box that you like a esky, if you fill that up with energy, well, it stays inside and you start cooking. So it's very important that things need to be looked in its holistic situation and approach. So we can't just rely on airtightness or in insulation or ventilation. We need to think about good building design as you describe it. And in Australia, it's definitely about external shading.
Anything to add there, Jess? No. Please.
Thanks.
Please project your voice.
I was probably picking up on the follow-up to that was, so before you do a blower door test on a house, in your slide, Sean was showing performance requirements, which were, this thing should be, sealed without any great performance. In the compliance method, which would take you down the Nathers path, there'd be some assumptions around the air leakage of the design. And also assumptions about behavior. Have you any comments about that? Do you think that needs to be looked at?
And the question is around assumptions around some of like the design software that's currently being used, like Nathers. So how does that sort of like figure into like the air blower door testing, and then also the assumptions around infiltration?
Sure, yeah. So just a couple of weeks ago, we went to the CSIRO-sponsored ARER conference. I presented there about blower door testing and how that factors into the energy models. So yeah, we know the guys at CSIRO. We know the guy, Michael Ambrose, who wrote that report about the average air tightness of Australian buildings. So this is an ongoing conversation, and basically my advice to them is that 30 years ago in the US, they said, this problem is way too hard to actually try to model with a computer. And you should just use basically some rules of thumb for your simulation. Make a much simpler simulation and then relate it to the blower door test, which is something you can actually prove. If you want to talk about energy modeling and the Nathers simulation, the Cheneth engine, which belies Nathers, we can talk about it if you want, but it's very unnecessarily complicated. And so yeah, you can get to the point we want to get to, which is better performing buildings that are more comfortable, more better performance with sound and energy, without resorting to very complicated energy modeling processes. So,
thanks, Sean. I appreciate that. Follow-up question: why is the door blower named after an American city? Is it Minnesota or Minneapolis?
Well, so. Thomas knows pretty much everything there is to know about blower door, the blower door guys. So I've known Gary Nelson, the guy who invented the Minneapolis blower door, for many years now, and I've been to Minneapolis to visit them. Thomas he's known Gary for a long time, so we know these guys who've been doing this since the 70s, yeah, I mean, basically. The reason that it lasted for so long is because it's a scientifically rigorous yet repeatable yet simple thing. It's just it's a solid concept.
Questions from the field? Yes? We'll get over there.
Is there any hope for people with dog doors? My dog door is 3/4 of the size of that piece of paper.
Yes, I can send you a link. You actually get now a Passive House certified cat and dog door.
Do you have to replace dog doors?
Yes. No, it's very simple installation. I'm happy to send you the link to the company. It's also available through a company, I think, called Laros in ACT now, so you can buy it there. It's available in Australia.
you write that on the board, please? Could you
Laros,
write that on the board?
L-A-R-O-S. L-A-R-O-S.
Well, that also kind of creates an interesting conversation because, like, as you guys have been interacting with also maybe the general public as well as people in the industry, is there a lot of pushback on like our lifestyles? So airtight building, is it going to impede on how we would like to live in our buildings? Like, you guys must have heard of a lot of kind of different feedback. So what kind of stories or reservations do people say to you guys?
People think they can't breathe in an airtight building, which is kind of silly because spaceships. How do people survive in spaceships for a long time? There's not much air leakage going on there, thankfully. Like, this is understandable stuff. It's not that complicated, right? Right?
But it actually could be. It could be for some people. You know, especially if they haven't been exposed to sort of like the ideas or anything like that. So, how do you settle sort of their worries? Have you had experience in terms of some people being very worried, and you're like, okay, well, let's kind of go through it. You got a good one.
I've been asked this question for 10 years straight since I arrived on these shores. And a couple of things. First one, people think they suffocate if the power cuts. Well, what do? You open up your windows and doors. So easy. And
Wait,
yeah.
you mean if you make a building airtight, do you mean the windows are still operable?
Well,
Can you open the windows?
we actually often say to people, oh, you can't open the doors, and because like, I mean, we're talking about still quite a bit of infiltration that happens in the background. And the best thing for people to get over this fear or the assumptions that they're making is to actually have the experience to live in one of these buildings. And that's unfortunately a situation we find ourselves in at the moment in Australia, that we do not have a lot of very high performing buildings to that level that might be a super airtight structure as well. So if there's anyone out here who would like to go into business with me, I'm happy to propose a development where we build a duplex, where we have two houses, one to whatever standard, let's say Passive House Plus Adelaide Superstar. You want to do it with me? Excellent.
I've lived in high performance buildings and I know how to do that.
And you're still alive. Excellent. So the idea is to have one super high performing structure, and the next to it is absolute code bare minimum. And so we offer people 2 nights, the first night in the high performance building, second night back into the other one. They're going to sign on a dotted line by the time they leave the other building, guaranteed. But we haven't had the experience. So so in the UK, for example, I think nearly all of the schools are built now to Passive House performance level. Schools. Yeah? They provide suddenly a much more healthier environment. Just a last story from mine. When I started my university degree, the first building science lecture I had, the professor came in and he asked, who has mold in his or her flat? I'm not going to ask the question here. And 3 hands went up. And he said, you, and you, out. I don't even bother teaching you because your body is under constant stress. You can't actually take up what I'm teaching you here, so I'm not going to waste my time on you. Out. He kicked them out. Yeah? And here we have a market that is undereducated, doesn't have access to good technical information, enables them to make good informed decisions. Last story from mine. A friend of mine works for an insulation manufacturer in Europe. They manufacture cellulose insulation, paper-based, high-quality, blown-in insulation material. And the technical team had an inquiry from a German customer. And the customer inquired about what type of newspaper is used as a raw material for the insulation. Because this client didn't want to have a particular political spectrum of newspapers being used as a raw material. I think that's an extreme customer. And then we find ourselves here maybe on the other spectrum. Thank you.
Just anything to...
In my experience going into people's houses, I remember the first time I saw a thermal image of a house under pressure, and I just got the biggest kick out of it. And I think that, you know, the houses that I go into, the clients that I see get the same thrill, because it's bringing something into their awareness that they were not aware of before. So there is a huge lack of education, but one by one you go around and you tell people, and you watch, you know, you put a door seal on someone's front door and you watch the numbers on the gauge go down, and in their mind they're thinking, wow, you know, this is amazing, saving money on my bills, or I'm just going to get less drafts. But putting a number on something that's invisible is really exciting for people, and I haven't experienced all that much pushback. Actually, I think people get really excited.
Just that's the magic that I see of it. It's putting a number to something that's invisible. You can't see, but then once you can put the pressure on the building, and then you take someone around and you say, oh wow, oh, I can feel that. Oh, that's cold there. And then this over here, oh yeah, no, I always felt cold over here, but I don't know why. Just having people able to literally touch and feel this thing that they're experiencing that they couldn't experience before, that is the power of this. And it's the power to illustrate this to a homeowner, someone who suffers the whole time. And it's a power to illustrate this to the builder that's trying to do the right thing. They really do have, they want to deliver something that's high performance. They're just not able to do it. And this is something that makes them able to literally feel their problems.
Just, sorry, Ken. For the people who have not experienced the blower-door test, I think we should just start off with the group here when we talk about it. Would you be prepared to do like a field trip for the group here? So you set up the fans and...
Sure. Right, no, not that. Yeah, we can organise that. Sure.
Well, next time you do a blower-door test, you can invite some people to watch. I mean, seriously, that's what we would do. So my early days in the Energy Star Homes program in Massachusetts, we'd do a blower-door test, and then some developer or a council or city member would want to just watch. And so we'd do the test, and then they would just stand by and say, oh no, yeah, okay, yes, I get it. They just want to be there and touch and feel themselves, see it themselves. That is something you can help them do.
And that's, of course, something that ASBN can tee up as well. No. So, and I guess just summarizing a lot of that, it's really about giving other people tools to be able to rely on something that a lot of people will say that some quote-unquote green buildings don't really walk the walk, and this is probably trying to put an extra layer to that. And we had a question in the back.
Yeah, can I ask one of you folks at the front there to do a little diagram on the paper of the weather tightness layer over a typical Australian house, which is a timber frame wall with a truss roof going over the top, and how you put the sort of the weather tight layer on a construction like that?
So can we have a live art demonstration on try to make it in?
There's a reason why I'm not a designer. So you're talking about the detail for a wall?
The eave detail where the truss hangs out over the...
Yeah. So...
And the weather tight layer.
Yeah.
Is it conditioned attic, or is it...
The external.
Or the air barrier.
The external I'm interested in.
There's more than one detail. Starting off with roof construction, just the field. At the moment, we find the truss, and then there's something as a separation layer between the metal cladding, normally, let's say metal sheeting, and the truss, yeah? And some rafters, purlin battens. What do you call them, battens or purlin? Battens, okay. So, yeah. We just talked about before that during construction we have a lot of moisture already built into our framing. Yeah. So ideally, what we want to do is, so let's say our truss there. We want to install a suitable roof underlay, roof sarking, directly on top of the trusses. Then normally what we find, or what we should be looking at, is putting a kind of like a dummy rafter on top. I'll show you a cut through as well. Then you have your battens. And then you have your whatever roof cladding you fancy. We have this detail without the counter batten already for tile roofs. Huh? You have like battens directly on top of the underlay. And this has a couple of advantages. The first one is that when you have moisture in here, and wants to get out, so you need to have a diffusion open, permeable roof underlay, roof sarking. So you have the moisture going through here. And in the winter nighttime, you can have ice on your metal. So yesterday when I arrived, it was like 4 degrees or something in the morning. You would have, at the appropriate situation, you would have had here maybe 0 degrees. So you have ice forming on it. Has anyone had ice forming on their car windows? This morning? Yeah. So that's long wave radiation, especially when you have clear sky at night time. You see everything radiating out. And what we want is, hopefully I explained it, first we want to have some airflow, some convection happening through here. And airflow, as I said, can be bad, but can be good. In this sense, it's good. So you have air going in there, picking up the moisture comes from in and takes it out. Yeah, make sense? The other thing that could happen, of course, is that you have condensation forming here on the underside, and it will drip down, and will drip on top of the roof underlay, and it can physically run out.
So if you've got your barrier there in green, how does it get under?
No, the blue, sorry.
Oh, the blue's the barrier. Oh, yeah, sorry.
But it's important to understand this is not a vapor barrier, as Sean talked about. This is a diffusion open, should I say, breathable product. It's not that you can take the product and blow through. If you can, don't use it for weather tightness. Yeah? It just describes how the moisture. So for the first detail, that's this one here. The advantage of having the builder installing the roof sarking, roof underlay as soon as the trusses go up, you're immediately protecting the framing underneath. And you're also protecting the builders. You're taking them out of the wind and rain, and you're also taking them out of the sunshine. I was in Canberra in February, and I was on a building site. It was like 42 degrees. And I had the builders with chainsaws working on the roof. I was trying to find a shade somewhere. I don't know how that could still work. So that's that first detail.
Sorry. Before you draw the next detail, could you possibly draw an alternate of that first detail that's a little bit more in line with how Australian construction generally tends to happen, which is an anti-con blanket effectively upside down with the bulk.
Shiny side up or down? Who's for shiny side up?
Well, I'm talking about how it's done by builders here in South Australia.
Yeah, I'm just asking, how is it done?
Down.
Shiny side down?
Yeah. And then the blanket is directly underneath the roof sheeting so that we don't get condensation in that fabric that you've drawn. And then I think what the questioner was probably interested in was the junction at the end of the eave where you have the building wrap coming up the wall face and you got the blanket and you can't see
one thing at a time. We'll get there. So what we're talking about, standard Australian construction, is that we have our battens, purlins, whatever you call them, on top of the trusses, correct? Yes. Yeah, good. And then we have the shiny side down. And then we have insulation on top, like the glass fiber that comes with the product. Is that correct? Okay. And then you fix your metal cladding on top. Yep. That's what it looks on paper. What does it look like on site? What's the thickness of the insulation here? 0.1. What's the R value here? One, theoretically. What's the R value here?
Including the timber.
Well, yeah, the timber provides the R value. It's no R value. If you do the calculation of how the whole thing performs, you're not getting an R1 here. You're getting R 0.0 something. So now we're talking about winter nighttime. Moisture in here in the attic. See that moisture? Yeah. And this moisture goes up here. And why is the shiny side down?
It's shiny side down because they put the bulk up there to stop the noise of the rain. It's not supposed to be insulation. The insulation.
But we're hard on here, so if it rains, the sound waves just hit here. They
No, I'm
there,
saying that's the logic behind why they do it.
So
I'm
that's
not
the theoretical
saying I agree
idea
with
behind
that
it.
logic.
Okay, so the reality of what we're finding ourselves in, because in these areas our R value is close to nothing, yeah, and we have here 0 degrees Celsius. We have on the underside here, what's our surface temperature? 2 degrees. Right, what's our air temperature in the attic? A bit warmer because we have downlights and moisture coming in, so we might have 10 degrees Celsius temperature, and our RH could be 60%. Just making up some numbers here. Yeah, so you have 60% relative humidity at 10 degrees Celsius. The dew point of this is, without knowing the numbers, I think the dew point will be if you go below 4 degrees Celsius or something. So without having that calculate properly, I would expect condensation to form here. Condensation forming here and then dripping in there. Do you have insulation in here as well? And traditionally there was none, no? And we didn't have condensation problems. I would love to show some photos where I've seen that the whole framing here is going moldy, where someone just put an insulation blanket on ceiling level. Because what happens is that the moisture is still coming through here, but here your temperature is going down because of the insulation. And that increases the condensation here, and then that just drips down and just gets wet, and it's just like a spiral going downhill. Okay? Can I make a suggestion that, following Ken's overs, the eave detail and the wall detail I will draw up after we had this session. Is that okay? Thanks, Ken.
No worries. Thank you very much for that. We have another question in the back. Health issues without the proper ventilating. Yep. Can we speak to that, Jess, Sean?
Yeah, right. If you thought I was obsessed about blower doors, it's actually a lie. I'm obsessed about ventilation. So most of my professional career, I worked in New York City, and that is all we talk about is ventilation in New York. We don't care about the building envelope because it's so expensive to fix the building envelope on a multi-residential building. It's already there. You can't do anything about it. But the ventilation almost always doesn't suck, and that's the problem. So what we have with multi-residential buildings is very poor, like you'll have a exhaust fan at the top trying to pull even amounts of air from every apartment. There's two things sabotaging that scheme. One is very poor airtightness of the ductwork itself and very poor design of the registers and the openings for every apartment so that you should get even distribution from each. And the other thing is poor separation, poor compartmentalization of apartments from each other. So that because stack effect works really well in New York City high-rise buildings, it basically creates its own pressure regimes there where the people at the top are stinking hot all the time, leave their windows open. That leaves a hole at the top of the building, which then makes airflow even faster out of the top of the building. And then the people at the bottom are suffering because they're freezing cold because the air is rushing in the bottom. So compartmentalization of sealing apartments from each other, that's really important. Then once you do that, then you also retrofit the ductwork to make it very well sealed. I can talk to you for days about this, seriously. But I'll stop.
But just what kind of what sort of like health implications will come about without the proper ventilation as well? Are you able to speak to that?
I think that's Sean's.
Yeah.
Well, so we did a bunch of studies. So Stephen Winter Associates that I worked with in New York, that's a consulting firm that we did some studies with National Center for Healthy Homes. It's a national organization in the US that is concerned with this very topic. And they fixed the ventilation system and saw a decline in asthma rates in the treated homes. So we did a ventilation retrofit, so did duct sealing on the entire risers of one building and compared that to asthma rates in the other building. And you see a decline in asthma rates from the buildings where you tightened up the ductwork. Like tightening things up, it just gives people the willies. They think, oh, I can't breathe anymore. It's actually making things better when you get control over the airflow in and out of the apartments. That's what's actually finally giving you supremacy over these natural forces. So asthma rates declined in that particular instance.
Am I right in saying that the stack effect reduces the humidity inside a building and that creates lung irritations?
Stack effect just increases air exchange through the building, and depending on the climate zone, depending on the weather, the time of year, it might, sometimes of the year in the same building, it might increase humidity, like the summertime. Sometimes of the year it might decrease humidity, having increased infiltration. It's really, what you really want is not this uncertainty of whether the wind's blowing or not. You want control over the envelope and the ventilation system. That's what you're after.
So the question was about the perceived negative effects about air tightness, and I agree that if we're getting, we need to insulate, we need to make the buildings as airtight, so non-drafty, and we need to ventilate. And that all needs to happen on the same level. It doesn't make any sense to have an R10 insulation and then have no air tightness and no proper ventilation. So that needs to happen anyway. The way that we change this is one at a time, and as your job. You need to educate yourself, professionals in the building industry, and the information is out there. It's a bit difficult at the moment in Australia to get good technical information because often it's sales and marketing driven. So we're happy to give you links to the Department of Energy in the US, to all sorts of stuff that was done in climate conditions that are similar to Adelaide, Melbourne, Northern Territory, wherever it is. And you can then make an informed decision for yourself, but you become the point out there into the market to then educate people. And because public awareness campaigns are extremely expensive. And in the end of the day, if you're engaging with homeowners, people who want to have a house designed, built, commissioned, all they're after is four things. The first one is an energy efficient building, but that's not very personally tangible. That's some dollar savings. We're a cashless society, basically. If someone tells me I can save $100, I don't even know what the color of a $100 note is now. Yeah. The second thing is about comfort. We want to have temperature ranges maybe around 18 to 22, maybe here a bit more, 24 degrees. We want the relative humidity between 40 and 60%. That's comfort. That's personal. We can adjust that. The third thing that people want is a healthy home. We don't want to have mold in our buildings that is killing us. And the fourth thing is we want to have our investment protected, because normally a house is the single largest investment that individual does in Australia. So that's what they want to have. What are we delivering at the moment as an industry? Energy efficient? Comfortable? Healthy? Are they durable?
and there's a lot of areas there that can be improved. We had a question just down here.
Yep, howdy. Just from a practical point of view, can you, for Adelaide, for this climate, can you do an airtight barrier in one layer in general construction?
Well, you could ask Thomas, but why don't you ask Thomas? Because he's nodding yes, and I'm saying it depends on what you define as a layer.
There's different means to create airtightness, and there have been different approaches internationally. You might have heard about drywall approach, so the plasterboard layer was used as an airtightness layer. Again, that works really well, but as I showed in my demos in my presentation, you have penetrations through that layer. So how do you seal that off? And then the question is, what level of airtightness are you aiming for? So to get to what is currently proposed for the NCC 2019 of 10, you just basically tighten up a bit of what you're doing already. So it's not too complicated for the industry is actually delivering this level already. If you want to go between 10 and 5, as Sean was saying, there are very simple details that you can work through, basically stopping having massive holes, and then there's a few key things that you can do very cost effectively. If you want to go below 5, that's where you really need to detail airtightness properly. You need to really verify the installation of that airtightness layer during construction, and that's the blower door as well, and you need to test it. If you And the most important thing is, and it's one of the things I personally quite like about high performance buildings, is that everyone is involved from day one. There's no point of halfway, when you're already under construction, to think, oh, let's make it airtight. That's not going to work. Yeah, we need to all come together at the front, and the electricians need to know why they can't just rip out stuff and drill holes and take out insulation. Yeah, the plumbers need to know exactly. The carpenter needs to know all of that. Everyone needs to be informed, but it needs to be detailed on the plans to start with. If you don't have the details on the plans, the builders can't deliver that level. But it's super easy.
We do have. Thank you very much for that insight. We do have to wrap up sort of like a Q&A session, but I do just want to quickly, before we go, ask each one of you, in terms of air tightness and better performance, that's obviously things that a lot of people are trying to get their heads around. In the next, few years, 5 years, where do you hope it kind of gets to? Or what point do you want to get to in about 1 or 2 sentences each?
All right, well, I'll start by saying I'm going to get me an ASBN Ken doll, like a real advocate for the sustainable built environment. Man, you are so cool. And the Ken doll is going to have the awesomest little handkerchief.
So you've just
cool.
made me, so in 5 years, I'm going to be the mascot.
Oh, yeah.
Is that what you're trying to say?
Oh, yeah. Oh, yeah.
All right, well, now you got to pass on to Jess.
That's one thing. And the other is, I would please hope that you can give Jess every last blower door contract that you can, or Josh, or Mark, or any of the other blower door testers that I haven't met yet. Give them some solid work, because man, they are the ones who are going to change this industry. They're going to grab it by the leaks and really
Seal it up.
Seal it up.
Yeah. Jess.
How leaky is your house? I don't know, how leaky is yours? Well, I got 5 air changes. Dinner table conversation. I think
So you want more
what-
competition?
I want more conversation.
Yeah. Thomas, where are we trying to get to?
Everything we're talking about in terms of air tightness, WUFI, which stands for, forget about it, all the other things, in the end of the day, it's all about health. Yeah? There's a quote that I often use from Schopenhauer back from the 19th century. It's like, health is not everything, but without health, everything is nothing. So everything that drives us collectively here is to actually provide healthy buildings. That's what we have in common. And there's different ways of getting there. There's different construction methodologies, whatever. What my hope is for Australia is that, let's say, as a measurable goal, let's halve the hospital admissions of young children due to asthma attacks, whatever, that are related to their living conditions. If we get to that, then the mass market is there.
Anyone seen that VLux ad?
Yeah, what?
The VLux ad with the little girl and she's standing in a box and they're showing you like the indoor generation and you know she's in a tight box with no doors or window, no openable sections, and then they're lighting candles to make the bad smells go away and spraying air fresheners and it was a really impactful ad. And then at the end of it, I think that Brett I was talking to, there's at the end there's a skylight that opens and lets natural sunlight in, and it's like this moment. You should look it up on YouTube. It's a really cool ad.
Anyway, well, join me in thanking Sean, Thomas, and Jessica for joining us tonight.